This is going to be more examples in using substitution to find antiderivatives. So far we've just looked at examples like this where we could change our integral, just move things around a little bit, maybe supply a constant, but we could turn our integral into something that looks like this. F of u of x times u prime of x dx. And sometimes we had to supply a constant out here to do that, but that's okay. We could have some constant out there. Or in other words, we've been able to make our integrals into f of u du, because we said that the differential of a function u is u prime of x dx. So we have been trying to choose u, look at our integrand, and choose u of x so that u prime of x dx with maybe just an additional factor of a constant would turn out to look just like this, and we would integrate. If we knew an antiderivative of little f, we would just use that antiderivative and plug back in our x if we didn't already have it, and add the constant. So those are the examples we've been doing, and now we're going to do a couple where when we look at it we try a substitution but it doesn't fit that exact pattern. So in that case we do something a tiny bit different. Okay, so here's the first example. We would just look at this and try substitution. It's usually the first technique of integration you try. And I would let u of x be the denominator. So let's see, get a different color. Let's let u of x, or u, be equal to 1 plus x, giving us the differential of u is 1 dx, or du is dx. So what I see here is that I have u here and du here, but I have this extra factor of x, and this will not just fit the pattern that we had in the last examples. So what I do in this case is I want to change the entire integral into a u integral. In order to do so, I have to solve for x. So that's easy. Just look, if u is 1 plus x, then x is u minus 1. And dx is du, and 1 plus x is u, so I'm ready to change the integral in terms of u. X is u minus 1, the denominator is u, and dx is du. So this changed nicely. Now why would I want to do this? Why is this better? Well, let's just go back and think about something we've known ever since middle school. If we have a plus b over c, we can split using the numerator. We can split it into the sum a over c plus b over c. Whereas if we had c over a plus b, well, we're kind of stuck. We can't simplify that any further. So the advantage to this is naming the denominator as u, which will give us one term in the bottom, and possibly, as in this case, we will want to split using the numerator. U over u is 1 minus 1 over u. So we have the integral of 1 minus 1 over u du, which we can integrate term by term. I could separate that into the difference of two integrals, but I don't need to write that out. Another way to say it is integrate term by term. So the integral of 1 du is u. We're integrating with respect to u now. The minus the integral of 1 over u, natural log u in absolute value. And now we just stick back in x. U was 1 plus x minus the natural log of the absolute value of 1 plus x, or x plus 1, plus a constant. should get back 2x over 1 plus x. So let's try something much the same. Notice here we're kind of looking for an inside function, you could think, or it's natural that we would call u 2x plus 3, because then we would just have a u to the 1/2 in the denominator, which would pop up in the numerator and be u to the minus 1/2. So let's try to and sometimes these things don't work, but I think it will here. If u is 2x plus 3, its differential du is 2 dx. Now notice here we have the integral. On the bottom we have the square root of u, and well, I could solve for dx if you want. Dx is equal to du over 2, so that I could just directly, instead of dx, put du over 2. But I need x. X is, I have to do something. I have to solve for x in terms of u. So solving for x in terms of u, we have 2x is equal to u minus 3 using u. And so x is equal to 1/2 times the quantity u minus 3. So I just put that right up here. 1/2 times the quantity u minus 3. Now I have a factor of 1/2, and I also have a factor of 1/2 here. So I'm going to pull them both out, and I have 1/4 times the integral of u minus 3 over u to the 1/2 du. I can split now using my numerator, same as before, and my denominator is just a simple one term. So this is 1/4, and now we'll split this into u over u to the 1/2. Subtracting exponents, we have u to the 1/2 minus 3u to the minus 1/2. I write it that way because I know that I will use the power rule to integrate both of these. So that's my integrand in terms of u. Now I integrate in terms of u, and I have 1/4 the integral of u to the 1/2. Well, I'm leaving a little space on the left, see, because I know I'm going to put in the reciprocal of the new exponent. Adding 1, I get 3/2, multiplying by the reciprocal. Minus 3, again I leave a little space. Add 1 to the exponent, I get u to the 1/2, and multiply by its reciprocal, 2. Okay, so we could, let me see if there's any room here. A little bit. We can finish. So now we put this in terms of x and maybe simplify. Let's see, I would get 1/6, and u is 2x plus 3. 2x plus 3, the quantity, raised to the 3/2 power, minus, now multiplying by 1/4, I will have 3/2 u, 2x plus 3, the quantity, to the 1/2, and now I'll add a constant. So that is my antiderivative. Again, I won't do it in a video, but if I had time, I would differentiate that and see if I got back to my integrand. One more example. Here again, I want to, this is kind of complicated. I may have to put the integral all in terms of u. But again, I'd like this to be the square root of u, not the square root of 3x plus 2. Why? Well, if I have the square root of a sum, I can't write the square root of a plus the square root of b. I'm stuck with that there. So I would rather have this just be u to the 1/2. So I will again let u be equal to 3x plus 2, and du Okay, so there's different ways that you might want to do this. I'm always tempted to just give myself a 3 right now. Whoops, excuse me. I'll need 1/3 out here and 3 right here. So that right there is now du. Put a 3 in. This is the square root of u, and I'm going to need to solve for x. Okay, so I have 3x is equal to u minus 2. So x is equal to 1/3 times u minus 2. So let's write this all out in terms of u. 1/3 the integral of x plus 1. I'm thinking there's a better way for me to have done this, but u minus 2 plus 1. Okay. This is kind of a mess. I'm going to show you on another slide what I should have done at the beginning, but this will work. I have u to the 1/2, and I put that 3 in right away to give me my du. Alright, so I have to simplify all this. So I have 1/3 the integral, and now I've got to multiply this out. So I have 1/3 u minus 2/3 plus 3/3, so it's plus 1/3 there. U to the 1/2 du equals, oh, I'm going to pull out that 1/3 here and make it 1/9, factoring 1/3 out of the sum here. So I have the integral of u plus 1 times u to the 1/2 du, which will give me 1/9 times the integral of u to the 3/2, multiplying it out using the distributive property, plus u to the 1/2 du. And now I will integrate using the power rule. 1/9 times u to the 5/2, raising it by 1, multiplying by 2/5, the reciprocal of the new exponent, plus u to the 3/2 times 2/3. And now I want to put that in terms of x. So we need more room again. And I will have here 2/45 times u, which was 3x plus 2, to the 5/2, plus 2/27, multiplying the 1/9 across, times 3x plus 2 to the 3/2, and I'll add a constant. Now I want to show you how to do this. This happens all the time. You start into a problem, maybe you see something you could have done easier. So let me show you this on the next slide, just where I could have taken a step at the beginning that would have made it easier. Okay, so I'll do this fast. Again, we let u be 3x plus 2, and du is 3 dx. And I see that the x plus 1 is definitely in the way here. So I'm going to split first and write this as the integral of x times 3x plus 2. I could put the square root, or I'll put 1/2 dx. And then I have plus the integral of 3x plus 2 to the 1/2 dx. So I'll integrate these separately. I'll split before I substituted in the u's. Again, well, and this time I'll do it by solving for dx. dx, I have du over 3, or 1/3 du. I need to solve for x because I'm going to need it right here. I need x, and that will be 1/3 first one, well, this is one like we did in the first lecture, but I'll just substitute in same way we're doing here. U to the 1/2 dx is du over 3. So the first one becomes 1/9 times the integral of, and I'll multiply this out right here. So I get u to the 3/2 minus 2u to the 1/2 du plus, and I'll pull the 1/3 out, and I just have the integral of u to the 1/2 du. Now you can integrate the first one term by term, and the second one, of course, is just a power rule, the second integral, and you see if you come out with the same thing. I sure hope that you do, but you can see that this was a little easier if I split in the beginning instead of waiting until I had put in all the u's. It's just less fractions in algebra to do. The last thing in section 5.4 is to see how we use substitution and evaluate a definite integral. There's two ways to do it. Let's integrate first. Again, letting u be the denominator, 1 plus 3x. du is 3 dx. I see I have an extra x in the mix here, so I have to solve for it. I get 3x is equal to u minus 1, and x is equal to then 1/3 times the quantity u minus 1. If you want to solve for dx, you can write dx is equal to du over 3. And then you can just take the dx and the x and the 1 plus 3x and substitute. So we get the integral of 1/3 times u minus 1. I think I did this. This looks like the first example. Over u, 1 plus 3x, times dx, which is du over 3. And I'm going to pull out the 1/9. I have the integral of u minus 1. This is the first example. Du. Okay, now the important thing to see here, we know how to integrate that, is to see what we do with the limits of integration. As you know, we're not looking for an antiderivative here. We're looking for a number, which is the signed area under the graph from x equals 0 to x equals 2. So we need an antiderivative. Well, we're getting the antiderivative, but I don't need to go back to x in this case. I can change my x limits to u limits. So if x is equal to 0, that would give us u is equal to, well, using our u substitution, 1 plus 3 times 0 is 1. And if x is equal to 2, the upper limit of integration, our u limit will be 1 plus 3 times 2, which is 7. So these limits of integration are from 1 to 7. And I don't have to go back in terms of x. I can just integrate, which we've already done. This was u minus the natural log of the absolute value of u. And it's 1/9 times that. And we're going to evaluate it between 7 and 1. So I have 1/9 times, now putting in 7, I have 7, u equals 7. 7 minus natural log 7 minus 1 minus natural log 1. The natural log of 1 is 0. So I will have 1/9 times 7 minus 1 is 6 minus the natural log of 7. And that's just a number. You could use your calculator to see what the natural log of 7 is. That's the answer. What I want you to see here is how you change your x limits to u limits, and you don't have to go back to x in order to evaluate. Now I've chosen a really simple example where the integrand is a line, and and I want you to see why this makes sense. If we're asked to integrate with respect to x from x equals 0 to 2, well, we would you'd probably just multiply it out and integrate, but let's do a u substitution. U equals 2x plus 1, and du is 2 dx. So this integral is simply the integral of u du. It's this right here. And notice if x is equal to 0, u is equal to 1. And if x is equal to 2, u is equal to 5. So we get our new limits of integration in terms of u. And we would integrate here, and we'd have, well, 1/2 u squared evaluated between 5 and 1. So we have 1/2 times 25 minus 1 gives us signed area of 12. Now if we integrated this in terms of x, we'd get 12. In other words, we find that the area would be 12 here, and of course it's 12 here. So what you're seeing is that what this substitution really does, the substitution u equals 2x plus 1, transforms one region into another region where the areas are exactly the same.